All right. And you know I'm a Winnie the Pooh fan. You should all read the original and Tao of Pooh. All right, so let's see what we got here. All right, so first order logic, you know I'm a believer in. You know, you want to read it from left to right. You say, let G be a girl, and then let B be an arbitrary boy, and then I have to prove that, right? I said, let G be Marilyn Monroe, right? And then I say, let B be an arbitrary boy, and then I have to prove that the boy loves Marilyn Monroe. That's the first one. And the second one, I say, let B be an arbitrary boy, and then I have to come up with a girl, and that girl depends on the boy, right? Depends on, I have to find some girl that the boy loves. Time complexity, we did a little bit about that. We did a little bit about adding, not very much. Not very much. Recurrence relations, you should be able to solve, right? You should know that the size of my input, right? I'm given an input of size n, and I want to know how long me and my friends are going to run, right? And then each friend, I have A friends. Each friend is given an input of size n over b, right? So T of n over b is how much that friend and all her friends' time they take, right? And so then I have A of them, and then this is how much work I personally do, right? Everybody should know that. You should know how to solve this, right? Do I have more slides here? Oh, here we got some stuff. All right, so we're on a roll on this. So in case I don't review this, how do you say, right? The top work, right, is n to the c, which equals f of n. Right? That's how much work I personally do. The number of base cases equals log A over log B. Right? Oh, no. Equals n to the log A over log B. Right? It's the number of base cases. So I compare this number to this number. Right? These are just, this is like 5, and this is, right? Each of these is a number. So I compare those two numbers, and if this number is bigger, then that's the answer. If this number is bigger, then that's the answer. If these two numbers are equal, then you add on an extra factor of log n. Everybody got that? All right, so here, universal quantifiers, right? You have the two players. We read them left to right. The prover produces the girl, the exists, and the adversary produces the for all, and the statement's true if the prover can always win, right? Holler if you don't know anything. So here I'll say, let x be an arbitrary number, let y be 5 minus x, so you can see my y depends on the x. And then we note, oh, look at x and y add up to 5, so the statement's true. Right? Holler, I'm going to just whip through these slides, all right? And your job is to be honest with me. Don't be shy about not knowing anything, because it's better than getting a 0 on the exam, right? So I'm going to whip through these, and the minute you think you're not quite up on it, say, slow down here. Slow down now. You're not going to, yeah. All right, he's going to want me to slow down. All right? We're going to be doing the entire course in 20 minutes here, so good luck. Right? Are people get this? Yeah? All right, so here's, when is a problem in poly time? Right? It's in poly time. What do I got? Oh, I didn't have anything. I don't have these memorized like I normally do. Right? So here, there exists an algorithm. How do I prove this is true? I want to know problem P might be sorting, right? How do I prove to you? And this would be a fine question on an exam. Slightly more for 2001 than for this course, but it's still a good question. Yeah? We'll get to, yeah, we'll do that, right? So I give you a problem like sorting. How do you prove that sorting is in polynomial time? Well, you give me an algorithm, and here the algorithm might be bubble sort, right? I'm not claiming it's the best algorithm. It's an algorithm that runs in poly time. And then I think, what is the running time of bubble sort? Well, it's n squared. So here I need a square. So I'm going to say let A be bubble sort, let C be 2. And then he asked, what's n0? Well, the official definition of big O is that if the input's small, then maybe the small cases are exceptions, right? So I'm going to say, well, my running time is only going to kick into n squared after I have 12 inputs, 12 numbers, right? So I'm going to set n0 to be 12. And then my adversary gives me an arbitrary input, right? And what needs to be true for this arbitrary input? My algorithm needs to sort, and either the input is of size less than 12, in which case I told him less than 12, I don't care about running time, or it's bigger than 12, in which case the running time has to be at most the size of the input he gave me raised to the power of 2. Right? Everybody follow that? Then the running time has to be at most the size of the input raised to the power of 2. 2 is the C that we got from over here. How does he even try to keep up with me? How do you guys try to keep up with me? Are you following this? All right, good. How do we sum arrays? How do we, right, so time is a function of input size, right? So if the input is an array of n numbers, then the size of the input is n, and the running time, right, if we just look at all these n numbers, is n. So look at the time and the input size are about the same. So we say it's big O running time, right? Do I got more here? All right, so there, right? Here the size is the same. But now if I'm trying to factor, right, what I'm given is I'm given an integer. And what is the algorithm? Is to count up to that integer, right? I want to factor, I want to know, you give me 1,000,003,000, and I want to know, can I factor it? Right? 1,000,003,000 sounds prime to me, but maybe it's not. Maybe they're factors. Maybe 11 divides into it, right? So I try dividing everything into it. And so what's the size of the input is only the number of bits to write down 1,000,003,000, right? But my running time is the value of 1,000,003,000, right? So that's why it's exponential time. Everybody getting that? Yeah? Up here, the size, we have so many objects. And the size of the input is going to be the number of objects, right? If I'm going to give you the objects, then, right, then the cost to me is I have to give you all these objects. So the cost to me is the number of objects. What's the cost to you? You got to add up the objects. So our costs are about the same, right? You're talking about the number of bits in each object? Yeah, so I'm putting that under the carpet because I'm looking at two cases. One where I have a bunch of objects and each object is a reasonably small number. and another example where I have one object and it has a lot of bits. Right? You're trying to say, let's do a weird trade-off between my two examples. And yeah, we could have a weird trade-off between these examples, and I'm not going there. All right? I'm looking at the two extremes. Does that make sense? Lots of small numbers or one big number are the two extremes. And one is linear time, and one is exponential time. And if you did some weird thing in between, then it would be some weird thing in between. All right? Everybody good? All right, so how do you add? Basically, if I'm trying to, let's see, do I have a bunch of things here? Oh, you should know that's called to get the chalk while cleaning up the blackboard, right? What's 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, right, up to n cubed, right? So these versus what's 5 to the 1 plus 5 to the 2 plus 5 to the 3 plus 5 to the 4, right? So I think you should be able to add these two up, right? And I used to spend lots of time teaching this, but now I think I spend minutes teaching it, and they didn't learn when I spent lots of time, so you probably learned just as well. All right, so here's the moral. The moral is these terms, they don't grow that fast. Let's look at here. We're going out to n to the 4, and here we're going 5 to the n over 2 to the 4, 5 to the n over 2, right? So here's the biggest term, right? That's the biggest. And here's the middle term, right? Middle, right? Everybody get that? The one in the middle, n over 2 to the 4, 5 to the n over 2. Right? Now, you'll note these two, right? This one equals a half to the 4 times n to the 4, right? And this is just a constant, and we don't care about constants. So if you don't care about constants, the middle term and the last term are about the same, right? So, and how many terms are there? Well, okay, it's true these ones are little and they don't really matter. But we could say that we have n over 2 terms going, n over 2 terms going from the middle to the end. Or we could say we have n terms going from the beginning to the end. Right, but that's just a constant. So the number of terms is either n over 2 or n, we don't care. And all the terms are into the 4-ish, right? So that's what the sum is. Order into the 5. Everybody got that? Now, no, he doesn't get it. He doesn't get it. But here, if you sort of play around, you go from this number to this number, you square this, right? If you take this number and you square it, you get this number, right? So this number is way, way bigger, right? When we're talking about adding it up, this number just doesn't matter, right? So the sum is order the last number, right? That's what I got, and that's what this says here, right? The sum, if they don't grow too fast, if they grow fast, it's order the biggest number. If they don't grow too fast, it's order the number of numbers times the biggest number, right? And down here, now we're doing another example. We're doing 1/5 to the 0 plus 1/5 to the 1 plus 1/5 to the 2, right? Here, these two examples are both, the terms are are changing quickly. So I say the sum is order the biggest term, but this is the biggest term here, while this is the biggest term here. So this one is order 1. Yes? Last example. I think you know what it is. 1 over 5 to the 0 plus 1 over 5 to the 1 plus 1 over 5 to the 2. Right? So they're shrinking. And so just like this guy, it's here in the middle example, half the terms matter, right? And here, well, only the biggest term matters. And here, this is the biggest term. And here, this is the biggest term, right? Everybody got that? That's everything I want you to know about summing. All right? So we did this already, right? We did that over there before we erased it. This one, the size of the input I give to my friend is just one, constant smaller, right? So what's the difference? Here, my friend's inputs, I keep dividing by b, so the depth of friend is logarithmic, right? So the fact that it's here, because of the a's in the front, I have a friends, they have a friends, so I have a squared grandchildren, right? So the number of friends is growing exponentially, but in this case, it doesn't matter so much because the depth is only logarithmic, right? If you grow exponentially for a logarithmic depth, then what you're going to get is n to some power, right? You're going to get a polynomial, right? What this constant is up here, the log a over log b, is you can see it's the fight between the b, which tells you how fast we're shrinking, so the depth, and the a, which says how fast the friends are growing, right? That fight tells you what the time will be, right? But down here, the number of friends is growing exponentially, but the depth is linear, right? So unless the number of friends is 1, do not do this, right? You hear what I'm saying? Because it's going to be exponential. All right, meta-algorithms, right? In each case, we try to have a meta pattern that you learn this pattern, right? And I really do think it's useful because back when I taught with other people, they would, we would learn a bunch of algorithms and then they would throw this thing out at you and I was like, how were they supposed to figure this out, right? So at least if we have found a pattern, you can be like a machine learning and find the pattern, right? To try to get the big structure right. Try to match the parts of the new problem with the parts of the meta problem, right? I keep emphasizing, right, what do you want to do? If you want to do well in this exam, the first thing you do is you memorize all the meta steps. Go to the steps pages and have those down, right? That's the first step. And so when you're giving your answer, it should look like that. Now, the thing I confess that makes it hard for you is that when I was writing them up, when I was writing those steps, I didn't know how many details to give because sometimes what I have in the steps is longer than you should write on the exam, right? Why? Because I tried to explain it as I went, right? It was a balance between, right? In general, some of my answers are longer than you need because it's a balance between trying to teach it to you and trying to show you what I want on the exam, right? So you're going to have to make some judgment there as to what to put on the exam, right? Oh, let's talk about that for a minute. Running time, not running time of algorithms, running time of you, right? So we've had 4 tests, but really there's 5 tests because we missed one. right? And there's actually kind of 6 tests because there's the first order logic stuff, right, and the summing. So, and there's 7 because there's the NP completeness stuff, right? So the tests you've seen so far, some of you worked on them for 2.5, 3 hours, right? And on the exam, we're in a very rigid place. You're going to have to do all 7 of these tests, and you're going to have to do them in 3 hours. All right? So be very conscious of your time. Right? So let me tell you a strategy if you haven't figured it out yet in your life. What I always do when I have an exam is I say, how many marks are there? I'll tell you how many marks there are. There are 102. Right? Tell me how many minutes you get. Right? You get 60 times 3, whatever that is, 180. Right? So you divide. You get how many marks per minute. Right? And then if a question is worth 20 marks, you do the calculation to how many minutes, and don't spend more time on it than those minutes. Right? You say, oh, this question's worth 20 marks. That gives me, I don't know, we should do the math. Maybe that gives me 30 minutes, right? Watch the clock. Try to say, what can I write in this space that will impress Jeff the most in 30 minutes, right? And then go on to the next question, right? Then go on to the next question. You hear what I'm saying? So, and then I didn't quite finish my other spiel. You learn the steps, right? So your first, I got 30 minutes. The first thing you do is you say, I have to put in the steps in there. And then the second thing you have to do is and you want to do these in parallel. So you first really read the question, right? And if it's I'll tell you whether it's a dynamic programming question or whether it's a greedy question, right? So the first thing you should memorize for every type of problem is you should memorize what is it that I'm supposed to be looking for in the question, right? So, for example, if it's a greedy algorithm, I need to know what is the input. I'm expecting it to be a sequence of objects, right? But let's not do greedy. Let's do dynamic programming because that's the test on Wednesday, right? You say, what's the input? Well, here, and like the greedy algorithm, the input's going to be a bunch of objects. And maybe in the dynamic programming, the input's just one object, right? But it's likely a bunch of objects, right? So anyway, the first question you should ask is, I read the question, what is the input, right? The second question you should ask is, what is the solution? And in both the greedy world and in the dynamic programming world, try to think about the solution as a sequence of decisions, right? In the greedy world, it's definitely each object, I have to make a decision about it, right? And maybe that's true in the dynamic programming world. There are a bunch of objects, and each object I have to decide whether to take it, whether not to take it. But maybe it could be something different, right? Anyway, so a solution is a bunch of objects. So you have to ask yourself, what is a solution? Right? Get a real feel for what the solution is. And then you have to say, well, when is this given a whole solution? Can I say, is it valid or not? Can I say what its cost is or not? All right? If the bird gave me a solution, would I know whether it was valid? Would I know if it was optimal? Right? So let's segue slightly into the NP world. Right? I want to know, is this problem in NP or not? Well, I just answered the question. if the fairy godmother could give me a solution and I would know in poly time whether it was optimal or not, whether it was valid or not, then the problem's in NP. Right? That's the definition of NP, is if you give me a solution, I know how good it is. Right? So that's what we're doing in the greedy world, and this isn't completely out of, the NP thing wasn't out of line of what we're doing. Right? You give me a greedy problem or an NP problem, and all of, or a dynamic programming problem, all those problems are in NP. They happen to also be in P. But why are they in NP? Is because I know what the inputs are, I know what a solution is supposed to look like, I know when that solution is valid, I know when that solution, what the cost of that solution is, I have a sense of what it means for that problem, the solution to be optimal. It's because it's better than every other valid solution. Right? Everybody getting me here? Right? So, and then you're going to be thinking about, well, how does the bird fit in, right? The bird tells me something about the end of the solution, and then I asked a friend about the rest of the solution. So you think about those key, think about when I give you a set of steps, it has a bunch of hooks that you need to hook into, right? What is an input hook? What is a solution hook? What is the cost of a solution, a valid of a solution? What do I ask the bird hook? What do I ask the friend hook? Right? These are various hooks. You should know what the hooks are, and you should be going through yourself saying, for this question, what are those various hooks? What do I fill in reader's comprehension into those hooks? Right? So then when you're writing out your solution, you should be able to do it really fast, right? You might be panicking now that, can I possibly do this on the exam in 3 hours? But my experience is people generally are, right? You ran through one, you're going to do a dynamic programming tomorrow. We'll try to make it work so you can do it for 3 hours if you need to. It'll give you experience. But then my feeling is either you can do it or you can't do it. And if you can do it during the exam. And if you can't do it, if you had 10 years, you wouldn't be able to do it, right? So really, all what you're needing to do is to write down the solution, write it down, copying the steps while filling in those hooks in the right place, right? In fact, if I'm not mistaken, when I was writing out the steps, I tried to put bold. Hey, this is a hook. You got to fill something in here, right? So fill those pieces in. So my feeling is that in the time allotted for the test, you should be able to write down the steps with as many of the hooks filled in as possible, right? If you've been paying attention at all and have any memory whatsoever at all, you should be able to do that, right? And then you will pass. In fact, you'll probably get a B, right? And then, now there's various places where you have to fill in little proofs, right? How do you say, well, if it was valid, it's, if ST minus 1 was valid, then ST was valid. That's a little bit of a proof. Well, so you'll need to do that if you want an A, right? I really think this course is reasonable, right? Somebody had a question and I didn't listen to you. Oh, an NP, so what is, so when we did Dijkstra's algorithm onward, from then onward, we defined what an input was. We defined what a solution was. We define, if I told you the input and I told you the solution, I told you whether this was a valid solution, right? This is all in my little question, right? I'm defining the problem. I define if I tell you the input and the solution, what's the cost of the solution? Right? This is all given. Right? And then what's the problem is given I find optimal S. Right? That's everything we've been doing since Dijkstra. Would you agree? Right? So what are we going to change? We're going to put these, we want to change the problem into a yes-no problem. Right? So we're going to combine these, and we're going to call valid prime IS to mean, well, it's valid, and the cost is at most 1,000,000. That's only 1,000, but we can put more zeros to make it 1,000,000. Everybody got that? You know, I fixed some number. And now, this is a yes-no question. Right? Now, so this is either it's valid. If it's valid, it means it has a sufficiently good cost. And now, I'll say I is a yes instance if there exists the solution such that valid IS, right? So inputs are yes inputs if there's a valid solution, right? Are you following this? And you put in a different word there, complete. Remove the word complete. Yeah. Yeah, so you take any problem of this form. Would you agree everything we've done is of this form? Right? So, where it's easy to compute whether it's valid. It's easy to compute whether it's the cost. What's hard is finding the solution. That's the definition of NP. Definition of NP is problems where there are various solutions, and given a solution, it's easy to compute whether it's valid. It's easy to compute its cost. What's hard is there an exponential number of these, and it's hard for me to find it. That's the definition of NP. Non-deterministic polynomial time. If I guess the solution, then I can verify it quickly. Right? But the non-determinism is the guessing, and the polynomial time is the checking. Does that answer your question? Other questions? Everybody good? Should we keep going? What? So let me tell you what we really want to do. When we go here, when we go from here, this world to this world, we're going to change the input. Let's define I prime to be IC. So the input we're going to have is some input from over there and some C. Right? And then I'm going to say I prime, and remember I prime is I and C. And then I'll say this I prime is a yes instance, right? I prime is a yes instance if the I is valid and the cost of the I is at most C. Right? So think about the 1,000,000 as part of the input. I should have said that instead. But I didn't want to get too nuanced. Everybody good with that? All right. That's Mika climbing. He's getting married in October. He said he was gay all growing up, but he's marrying a woman. So go figure. So loop invariance, right? You should know all these steps. You should know, I'm going to tell you what the precondition is. I'm going to tell you what the postcondition is, right? You fly in from Mars in the middle. Why do I say I fly in from Mars? You know, if there was one theme that is going through my religion of ranting to you is don't try to think about the whole problem at once, right? And so somehow you have to break it down to little tasks. And the one way of having little tasks is by this flying in from Mars. I'm not worrying about the past. I'm not worrying how I got here, right? Maybe the fairy godmother brought me here. Maybe the little bird brought me here. Maybe I just fell in here from Mars. I don't know how I got here, right? What do I know? I'm promised that the loop invariant's true, right? I'm promised that, right, I've made some sort of progress maybe, but I don't know what, and there's an exit condition, and I haven't quite reached the exit condition. And what's my goal? My personal job is not to get to the post condition, not to understand or micromanage the beginning or the end, right? Because if you try to do that, you're going to drown, panic and drown, right? So all you need to do is take one step while maintaining the loop invariant, right here, while maintaining the loop invariant and while making progress. Right? Everybody got that? It's a really, I joke that it's a religion, but really you want to get it in your soul because I think that is really how you solve algorithmic problems. Right? So then what else do you need? You need how do I establish the loop invariant? Right? I need the measure of progress. What do I need about it? I need that it's not too overwhelming when I begin, and it's reasonable when I end, and it makes progress in between, right? Either it keeps going up, or it goes down, or it divides by 2, or it subtracts by 1. It does something reasonable between the two so that you know the thing exits in that much time, right? And then you need to know that right here, if the progress is good enough, then I exit. And you need to know that if at the end I've dropped out of the loop, what do I know? I know the loop invariant's true because I've maintained it. I know the exit condition's true because I exited. From those, I have to get the post condition, right? So, again, how do you do these? You know you're going to need these various paragraphs. You know how the paragraphs are headed, right? You know, right, this one here. You know you're going to write, I flew in from Mars, so I know the loop invariant's true. What do I know from the loop invariant? I know that these things are true. Oh, the exit condition's not true, so, well, that's not going to help me too much. But I write it down, right? Then I take some step. What does the step do for me? It moves me from the x prime variables to the x double prime variables, right? If the code says x equals x plus 1, then x double prime equals x prime plus 1, right? Everybody know this? So I know where I'm going to be in the next step. And so then you have to, and then you write down over here, what do I need to be true at time t plus 1, right? So over here I have what I have, over here I have what I need. And then this is where you get the A+. You know, you do your best hand wavy to get from there to there. Right? Everybody good with that? Partial correctness. If I stop, it says I establish the loop invariant. Right? These are the paragraphs that I need. Right? I need a paragraph that defines the loop invariant, defines the exit condition. Either I give it to you or you give it to me. Right? And then you need a paragraph which says this. How do I establish the loop invariant? You need a paragraph which maintains the loop invariant. Right? You need a paragraph which gets the post condition. And this says, if it stops, then I get the right answer. Right? And then usually, does it stop is easy because the measure of progress is obvious. So probably I will ask you, what's the running time of this thing? And you convince me that the running time is n squared, in which case you've kind of proved to me that it stops. Not only do you prove to me it stops, you prove to me it stops at n squared time, right? So that's, how do you do that? You have a measure of progress, and you know the measure of progress it starts out at n squared. Maybe the measure of progress starts out at n cubed, but it decreases by n every step, right? I don't know. So then the running time is n squared. You do some math like that, right? That was a dumb example, but it would be an example, right? Everybody sort of follow that? All right. So here's this example, right? So how do you come up with the loop invariant? Well, you say, well, I need to sum up all the way up to capital I, so what's true in the middle, right? They're all kind of ask the fairy godmother for what you want. In the middle, what do I want? Well, I wanted to have summed up the first so many, right? So that's your loop invariant, right? And it's a picture, not an action, right? So you define the t's and you find the t plus 1s, right? And how do you come up with the code? Remember, I had various exam questions that people were flopping, right? And so then I added new slides. And what do the new slides say? Well, focus on two pieces, right? I'm here, the loop invariant's true. I have to do two things. I have to make progress, and I have to maintain the loop invariant. Right? So the first step, say I have to make progress. Well, what's my measure of progress? Well, my measure of progress is the letter I, the little I. Right? So if I want to make progress, what do I have to do? I have to increase I by 1. Right? All I have to do to make progress is to say I equals I plus 1. Why? Because I is my measure of progress. Right? But what did that do for me? That I made progress. I'm closer to the school. But the loop invariant's no longer true. It's no longer that S is the sum up to my current I. It's the sum up to my previous I. So I have to get back on the path. Right? And I think if you think about it in that sort of steps, I mean, this is such a trivial example that you think this is dumb. Right? But you can imagine a harder problem. Right? Harder problem, the measure of progress is complicated, and the loop invariant is complicated. But if you break it up into two steps, I have this data structure which meets the loop invariant. What do I have to change in the data structure so that my progress goes up? Do it. Now, is your loop invariant true? Probably not. So what do I have to do not to decrease my progress, keep the progress solid, and get back on the path? Right? People following this, you can see how it helps a little bit to breaking down the steps. Everybody good? So that's our progress. Right? How do you maintain the loop invariant? You add the next object back in. Right? And by formalizing, right, we have a formal definition of IT and of IT plus 1 and FT and SD plus 1. We have a formal definition that ST is the sum up to IT, right? So then when I increases, we know what we have to add on is the new value, right? And there's this whole balance between, when other people teach, they focus on details, and I focus a lot on hand waving, right? Well, when do you need the details, right? You need the details when you need details, right? Do I add on the IT squared? Do I add on the IT plus 1 squared, right? So here are the details that are necessary to move along. People following this? I think we said all of that. I think we said all of that. This was a fun example, right? Right? What's more of the input? Right? The more of the input says that the loop invariant says, it's a picture, so I don't want it to sound verby, right? But the picture is, we've so far, I've flown in from Mars, and the people before me, they've looked at this part of the input. And what have they given me? They've given me whatever the solution would be if that was the input. Right? That's what I have. I have, if that was that 1 through I was the input, what is the solution? And, well, maybe I have some extra information than I need. This is all back to kind of like when we do recursion. What do we need from our friends so we can keep going? Right? Whether you're asking the previous people or we're recursing and we're asking our previous friends, what extra information do we need so we can move ahead? Right? So we have this extra information, and then what do I have to do? I have to take the next object, pretend it's include it in the input, and then change my friend's solution to my solution so it includes the next biggest, right? In fact, doesn't this feel kind of like what we do with, in some ways it's greedy algorithms, we're changing one solution to another. But what was the difference there, right? Here's the key difference. With the greedy algorithm, we don't have the solution. The fairy godmother has it. And it's not a solution to the sub-instance. It's a solution to the entire thing, right? So, sorry, they're not the same. I was about to say, doesn't that feel like the greedy algorithm? But it's very different, right? So I take it back. It's not the same at all. Don't say they're the same. All right. More of the output. What's the more of the output? My friends have produced the first I objects of the output, and my job is to produce the next one. Right? That's all there is to it. Narrowing the search space. All right? This is an important one too. So what we're doing is we're looking for something. And the loop invariant will be, and I forgot always to say this part of the loop invariant, is, well, either we have found it already, or we haven't found it. And if we haven't found it yet, we say, if it was anywhere, maybe it's nowhere. If it's anywhere, then it's in my narrowed search space. Right? So that's a good loop invariant. Keep it in mind. Everybody get that? And how do I make progress? Well, I know it's in here. If it's anywhere, it's in here somewhere. So maybe I look a few places, and if I find it, then we found it. But if we didn't find it, then I somehow narrow the search space. Maybe I cut it in half. Maybe I make it a little smaller. Maybe I make it smaller this way. Maybe I make it smaller this way. Right? I make it smaller. And then I have to prove, right, that the loop invariant is maintained. How do I prove the loop invariant is maintained? Well, if it's anywhere, then my friend assures me it's in here. And if it's in here and I did these actions, then I can be confident that, well, it might be over there as well, but even if it's over there as well, it's got to be over here too. Right? I'm not claiming it's not over there. I'm claiming that there's got to be one in here. Right? Everybody got that? Yeah? Good, good? So you're going to need that for sure in this world. What do we got here? That doesn't say anything. Recursion. We good with recursion? So we started with the scary example. Why did I do that? Just to start you with a certain amount of fear so that you would all pay attention. Right? So what do we want to do? Remember the big moral here. I'm given my input. My goal is to get a solution for my input. I want to do as little work as possible. I want to worry about things as little as possible. I don't want to get anxious. I personally spend a huge amount of effort maintaining my anxiety to be down. Right? I tend to be an anxious person. And if I'm going to worry about my friends' friends, right, then I'm going to get anxious. So minimize your anxiety. Right? So this is my input. What can I do? I have some measure of size of this input. What can I do with this size, with this input? I can give my friends, I can have as many friends as I want. And I can give them any input that meets the precondition as long as it's smaller. Right? What do? They give me an input back. They don't give me an input back. They give me the solution to their problem back. Right? How do they get their solution? I don't care. Thank you. Thank you. Right? I don't care. So I get the solution back. I combine their solutions to get my solution. Right? Everybody got that? And if my input's small enough, then I can have smaller friends. Right? Because my input's so small, and I have to do it myself. And that's it, guys. Right? And I'm going to give you some problem. And it really, what you ask your friend, you think, what is my input? Right? You think, what am I looking for? What can I ask my friends? Right? To help me with that. And usually it's obvious what to ask your friend. Usually. If I give you a binary tree, for example, I'll tell you right now who your friends are. Right? It's all the subtrees or your friends. So you get the answer from your friends. And now, what's the answer to my problem? And so maybe there's a bunch of cases and a bunch of tricky to get from my friend's answer to my answer. Right? And that's another little box where you do your best to hack it together. Right? Right? So you're worrying about just one guy. Right? And I think we said all of those things. Right? This is just, right? How do you use strong induction then to prove that if everybody is just trusting their friends, why does the whole thing fit together? Right? Everybody kind of appreciate how strong induction then does that for us. Right? Because what does strong induction say? Strong induction says, do things work for me when they have size S? Well, I trust that it works for me when it has size anything smaller than S, and then I prove that if it works for my friends with things that's smaller than S, then it works for me with things of size S. And here I shouldn't have said S because that's S. I should have said I. I have size I, anything smaller than I. Right? Everybody good? Running time. We did this already, right? Remember, this is what your code needs to look like, right? I have an input. What I give to my friends they have to meet the right? My input meets the precondition. What I give my friend meets the precondition, right? What my friend gives me meets the postcondition. What I give my boss meets the postcondition, right? Right? I take my input, I break it up into parts, and I give them to my friends. I take the inputs from my friends, I combine them to get my input, my answer. Right? Everybody got this? So have your code look like this. There's no excuse for the kind of stuff I've gotten from people in the past. Right? There's no excuse that it shouldn't look like this. The only time you should have a loop. What's the only time this thing should have a loop? What? When you're drinking. Exactly. When you're drinking. When you're drinking. That was a very good answer. I'm going to give you one extra caveat. Suppose the only other example I can think of is when, say, the input's a tree and I don't know how many children I have, right? If I don't know how many friends I'm going to have, and then instead of having friend 1 and friend 2, I might have a loop over my friends. Right? Does that make sense? Oh, and the other thing that you may have to do, and I can't remember if you have to do it or not. I have made up the exam, by the way. Is you might have to get more help from your friends. Right? If your friends aren't giving you quite as much information as you need, then you can say, you can change the pre and the post condition, right? So then if you do that, you have to very clearly at the top say, markers, I've changed the pre and post condition, right? And then you have to do it with respect to that. Everybody good? Recursion on trees. What do we know? Our friends are the subtree, and all we know about the subtree. We never go down there. We know nothing about the subtrees that our friends haven't given us. Right? In fact, let me tell you right now, if my input's a tree, then what you should ask is, I need the answer, whatever the question is. I need the solution for the entire tree. I know the root. I know how many children I have. And I'm going to get something from each of my children. The children are not going to talk to each other. The children, all they know is their subtree. Right? So you're going to say, friend, I know that all you know is the subtree. I don't want the entire tree because that would take too much. I want just ideally a constant of information about you that doesn't grow with the size of the tree. But what do I need? What constant information do I need from that subtree so that when I get that from each of my children, I can solve my problem? Yeah? Probably. I didn't read it. That's the first example we did, so that's probably. I could be asking, yeah, that looks like 6. Looks like the number of nodes. Yeah. So, for example, my friend is just a smaller example for me. So what information do I get from my friend? Well, the first thing I get for sure is if he had been the whole input, then he needs to know what the answer is, right? That's you need to for sure. So from here, I want to know the number of nodes. So the first thing I get from my friend is the number of nodes in his subtree, right? But maybe he tells me something else. Maybe he tells me the depth of the tree. Maybe he tells me the color of the tree. Maybe he tells me, right? Maybe he tells me something else, right? And if your friend is telling you those extra things, then you have to return the favor, right? Remember the whole pass it forward thing. Someone's nice to you, you have to pass it forward and be nice to your boss, right? If your friend tells you the color of his subtree, then you have to tell the color of your tree, right? Everybody got that? Right? I only know what the precondition tells me, right? What I get back is what the postcondition tells me, right? Everybody good with the recursion? Right, graph searches, right? What do we say? We have the obvious graph search algorithm is we have a loop invariant that tells me which nodes have I found so far. And a node is found means you've traced out a path to it, so you know it's reachable from S, right? What is our goal? Our goal is to reach every node visitable from S, right? And do something. Maybe just say hi to it. Maybe our goal is to paint it green. Who knows what our goal is? But our goal is to visit every node reachable from S. And so the found nodes are ones that if we reached, and one of the things that we know about it is it's reachable from S. Right? And the handled nodes, what's true about a handled node is that you have found its neighbors. Right? Everybody good with that? So what's the algorithm? You keep track of which nodes have been found but not handled, and you choose some node that's found but not handled, and when you do what? You do the obvious thing. You handle it. And what does handle mean? Is you find its neighbors. Right? So now its neighbors, if they were found before, they're still found. But if they weren't found, now they're found and not handled. Right? So, and now you can, what order do we, if we have a bunch of nodes that are found and not handled, we could handle them as a queue, which gives us breadth first search. We can handle them as a stack, which gives us depth first search, which is the same as kind of recursion, stack recursion, right? You could do it with a priority queue. You handle the one that feels the best, that feels closest to S, and that gives you Dijkstra's algorithm. Right? And you know Dijkstra's algorithm is what Google is running on your phone when you ask what's the best route to get from where I am to the beer store. Right? Everybody good? So here are the handled nodes, right? And what the handled nodes are the nodes that have been handled. The handled paths are the paths that go how long? Yeah. When I said that I made up the exam, what I said is I have a question for each thing, and I have not given weights to them yet. I would say the weights that I put on them will mainly be me communicating to you how much time you should spend on it based on how hard it is, right? So if I think the loop invariant question is slightly harder than the greedy algorithm question, I will give it more weight, both because you have to work harder to do it and because you should spend more time on it. I try not to have all of them record hard. I try not to have any of them harder than what you've seen so far on tests, right? And because that's the goal here. You're not going to find any surprises on this test. And sometimes I'll make one a little easier because there's a lack of time, and then I make it less marks. But how should you study? You should. They're all equal weights, right? Of course, the NP stuff, right? There's going to be a question, and I would almost, I think I pretty much even told you what the question and the answer is, right? If you were listening at all, you could know what the question and the answer is, right? So, and then first order logic, I try to slip it in when I can, like we did on the other test. The graph algorithms, right? I'll slip in little, there'll be a little easy question. And then the others are equal weight. Right here, what do you need to do? You have to say, well, what's the handled path, right? A handled path goes through handled edges, and then there's one last, because this is a handled node, then these are handled edges, right? One last handled edge to a node that's not handled, right? And what are our D values? Well, if the node has been handled, then we know the length of the best path, right? And if D has not been handled, we know the best length of the best handled path. So this path that goes like this might be a better path to B, but we only know the one through U so far, right? So really, I think we haven't finished these review slides yet, but so far at least, if you understand everything I say today, you can do as well as anybody on the exam, right? Because you think, should I know this little weird esoteric thing? Should you know it? I'm going to say, if I don't say it today, you don't need to know it, right? The only reason you might need to know it, if I happen to just ask that question, then maybe it'll be useful, right? So here, I'll tell you where I got this from. Somebody asked me, could I give you the test 3 that I've used in the past? This has been the test 3 question. This is what you see here exactly has been the test 3 questions for the last decade. All right? So what are you supposed to say? Where's the hard part? The hard part is the best path to one of these isn't, right? I think the best path to E is coming here. 17 plus 2 is 19, right? So people will say, well, everybody gets everything right except they may make this D value 19. Why do they make this 19? It's because the shortest path to it is 19, right? But we are only considering the handled ones, and this path hasn't been handled yet. Right? Everybody got that? That's the only thing is being tested here, right? And why do I keep giving the same example year after year? It's because if you've memorized, if you understand it, you'll get it right. And if you don't, right? And half the class keeps getting it wrong. So why not just keep giving the same question? Yeah? All right, so this 20, everything is fairly obvious here as being the D's are the shortest. We're looking at for the shortest path from A is S, from S to E, right? And what is that shortest path? Well, you do this. 13 plus 3 gives you 16, right? Plus 1 gives you 17. Plus 2 gives you 19. So you might ask, why isn't this 19? Well, instead, it's somehow you get here for 13. 13 plus 8 is, no, here, 16 plus 4 is 20. So why is this 16 plus 4? Well, because this is a handled path, and this is not a handled path. So what the D is, we've not looked at this edge yet. This edge, as far as we know, doesn't exist yet. So don't tell me that this is a 19 that relies on that edge, which we haven't looked at yet. Yeah? D, I keep saying. D, if it's a handled node, D is the shortest path. The weight of the shortest path. If D is not handled, if the node's not handled, then it's the shortest handled path, right? So in this example, this path, A, B, E, is of length 20, and it's handled. Why? Because A is handled, B is handled, so this edge is handled, right? These edges, this edge I looked at when I handled B, right? B is handled, so I looked at this edge and I saw that it was 4, and I updated this to being 20, right? But I haven't looked at this edge yet. Yeah? So what do we do next? What we do next is we handle the guy who has the smallest D value, which is 17. We handle its edges. And when we handle the edges, we update that to 19, and we update that to 17 plus 2. Right? That's Dijkstra's algorithm. And nobody should graduate without knowing Dijkstra's algorithm. It's the bread and butter of Google search, finding beer. Right? Yeah? You've found all its neighbors. Handled means you've handled its edges, and you've found its neighbors. Yeah, so what do we do when we handle this C node? We say, I can get here of distance 17, so I follow all its edges. I can follow this edge and say 17 plus 2 is 19. Oh, that's better than 20. So I update it. I follow this edge, it gives me 17 plus 2 is also 19, so that's better than infinity. Right? That's handling this node. Dijkstra's algorithm. Breadth first search, right? Breadth first search, we store, where are we? We store, they've been partially handled, right? You have a stack that stores for each node how many of the edges you've handled. And what do? You pop the top thing off the stack, and you handle its next edge, you push it in, and you push on what you just found. That's that for search you should know. We used it to find linear ordering, right? Network flows, right? It's an optimization problem, right? Look at, here we go. So what is the input? The input is a graph with capacities. What is the solution? It's the flow along every edge. Is it valid? Well, for every edge, the flow can't exceed the capacity. For every node, the flow in equals the flow out. What's the value of the flow? It's the flow out of S minus anything that flows back in, right? What is your goal? Is given a network, find the optimal flow, right? There's another problem that's of interest. Min cut. What's the input? Again, it's a graph with edges with weights, capacities. What's the solution? It's a cut, the partition of the nodes into two pieces so that S is on one side and T is on the other side. When is it valid? When is what I just said it was, right? When is it a cost? What's the cost of it? It's the capacity of the edges going from the U side to the V side, right? It's another two problems. I've just defined two problems, right? My father's girlfriend hung out with me yesterday, and we didn't have anything to do because all the kids were asleep. And we talked more about linear programming. And, right, because I was making slides about linear programming, and instead of reading books, I make it up. And so I was learning more how, she and my father were writing the books on it, so they were telling me some more about. So primals and duals, right? So here, the primal, right? So the question I had to her is, right, we use the dual to prove that we have a primal solution, optimal solution, right? How do I know? I mean, this is, okay, here's what I want you to know, right? I've said this already, right? What do I want you to know is if you have a solution, right? If I have a solution to the primal, right, I keep getting a better and better and better flow, right? And when I can't get a better flow, then the algorithm hands me a cut, right? And the primal, the flow and the cut have the same value, right? And why is that useful to me? Is that the flow witnesses the fact that I can achieve a flow that good, right? And the cut witnesses the fact that my flow couldn't be any better, right? People remember that? Yeah, so the flow witnesses that you can achieve a flow. And the cut witnesses that my flow couldn't be better, right? Because you can't cross this cut. There's a cut. I can't flow more than the value of the cut. Right? Everybody kind of get that? And the question I asked Kathy was, if I needed to prove that this primal has an optimal value, I would do this in linear algebra. And she said, yeah, people say that all the time, and they're right. But even the people in industry, they care about the dual problem and the solution to the dual problem because it gives you intuition for what's going on. She says that what is the primal problem? Is I want to optimize something subject to a bunch of constraints. And what are all these constraints? I can't use more than this resource and I can't use more than this resource, right? She said what the dual does for you is it kind of gives you a price on each of the resources, right? I have a limited amount of this resource, and hence, this is the best solution I can get. But if I could pay $50 and get slightly more resource, right, how much would I be willing to spend on my various resources to have more resources so I could get a better solution? That's where the dual comes in, right? So she said people who are in the industry actually do want the dual, not just to prove optimality. So that was a good conversation to have over breakfast, right? It's what you should always talk to your stepmother about. She also talked about how my father is being mean to her, but we won't get into that. All right. Exactly. This morning on the way here, I wrote this email that said, "Oh, Kathy, you're so wonderful to us all. We all appreciate you so much." And I sent it to her and my father. This little linear programming. So as I said, what is linear programming? It's exactly what I said. We're trying to optimize something. Right? Here I'm trying to minimize the cost of the hot dog, subject to these constraints. I can only have so much moisture. I can only have so much protein. Right? I have various rules. And so that's an optimization problem. And I didn't tell you, we didn't go into the whole thing, but given any linear program, you can take the dual of it, and as Kathy tells you, the duals will tell you somehow how important each of these constraints is. So that's, if you go into business and you're a company, you need to know linear programming. Greedy algorithms, right? Again, we have inputs is a bunch of objects. A solution is a decision about each of those objects, right? The cost of the solution, I don't know the cost until I have the full solution, right? I don't know whether the solution is valid until I have the full solution. Now, of course, if I have a partial solution, I might know it's not valid, right? But I don't really know until I get the whole thing, right? So a fixed priority algorithm. So remember what the algorithm does is it looks at every potential object out in the universe, whether or not it's in the input, and says how much it likes it. It gives a value to it. That's the greedy criteria, right? And then the fixed priority, that value is fixed. And then the input comes sorted based on this greedy criteria. And what do I know about the input? I only know what I've seen so far, right? I've seen the objects in the order of their greedy criteria, right? And I've made decisions about the earlier objects that I've received. I've made irrevocable decisions about them, right? And now I have to, based on just knowing these inputs so far, what I've seen so far, the decisions I've made so far, I have to make a decision, an irrevocable decision about this new object, right? Why do I have all these weird constraints on it being a greedy algorithm? It's because we want it to be fast, right? Why is it fast? Because I'm not worrying about the future objects. I'm just worrying about this object. I'm just making a decision about this object. Why is it irrevocable? Because that's fast. If I had to go back and change it, then we're likely doing recursive backtracking, and it'll likely be exponential time, right? If I just make a decision about each object, then here's a question that people kept asking me, and I kept saying, it's obvious, so it won't be on the exam. But then I thought, maybe it should be on the exam, right? What's the running time of a greedy algorithm? So I've heard some ins. Why would it be in? Is I look at each object and I made a decision about it, and ideally each decision happens in constant time, right? That's why the answer is n. Why is the answer n log n? Because you got to sort them in the beginning. See this word right here? Sort. Sorting takes n log n time. All right, everybody good with that? That's a fixed adaptive, a fixed priority. Adaptive priority is I've seen these objects so far. I've made decisions about these objects so far. Now, every potential future object I will give a new priority to, right? And I will get, what will the input machine give me? It will give me the next object according to the current priority, and I'll make a decision about it, right? Everybody good with that? There's the code, right? And what's our loop invariant? If you don't know the loop invariant yet, then you might as well go home, right? The loop invariant is the algorithm had made decisions about some objects so far. That's AT, right? AT is the decisions made so far by the algorithm. The fairy godmother, somehow we want to say that the algorithm hasn't gone wrong yet, right? How do we want to say that? We want to say there's still hope for the algorithm. The mom, the fairy godmother is his mother. Fairy godmother doesn't want to be panicking, right? She wants to have some hope for the future. And so what we need is that his mother somehow has in her mind some vision of the future in which her son still obtains an optimal solution. Right? It's a completely reasonable story that every mother understands. Right? So that's our loop invariant. AT is what the algorithm has done during the first time steps. Right? Oh, where's our loop invariant? And ST, what is it? It's a full solution. What do we know about it? It's consistent with what the algorithm has done so far, and it's a valid full solution, and it's an optimal full solution. Right? Everybody got that? It's consistent, it's a full, valid, optimal solution. Right? Everybody good? And who knows it? Does the algorithm know it? No. Does the prover know it? No. The fairy godmother knows it. Does she exist? I don't know. I don't know. Don't ask me hard questions. Right? Everybody got it? That's our loop invariant. There's at least one optimal solution, ST, that extends the choices made by the algorithm so far. Right? And how do we do it? Right? We please tell me again. So, you fly in from Mars. What do you know? You know that the algorithm has done AT and ST extends it. Then the algorithm makes another decision, which gives us AT plus 1. Right? Now the prover steps in. The prover tells the fairy godmother how to change ST into ST plus 1. And then that prover proves that it extends the new choices and the old choices, and it's still valid and it's still optimal. You all know this, right? Right? So here we make it, are we running out of time? All right, good. So, people can leave, people can stay, I don't care. Oh, let's talk about post-Wednesday, because on Wednesday people will be, first off, let's talk about Wednesday and post-Wednesday, all right? So on Wednesday we're going to be writing a test here until the class comes. Has anybody found a place for us to go? So I'm fine with us all just sitting on the floor out here in the hall. Right? If you want to work for more than an hour and a half, bring pants that you're willing to sit on the floor on. Right? Bring your work clothes. We're going to get dirty. We'll all sit on the floor. You won't sit next to somebody you know. You'll finish the exam. We'll sit there until we go home. Is that okay? All right? And don't tell my boss, because I don't know if it's legal. All right? Then post-Wednesday, what day is our exam? Is it Wednesday? So if people are wanting to come, I'm willing to come one other day. So think about what day that should be. Right? So let's... Oof. So the test is on Wednesday, you say? So the advantage of having it later is you've already studied and we can clear up your issues. The advantage of having it earlier is that then you can still study for it after I tell you stuff. But I'm not going to tell you anything that I haven't already told you. So I don't care. When people yelled out days and I wasn't listening. Monday. Any other votes for different days? Friday over here. Well, that's pretty soon. I mean, we're here already. Right? Are we saying Monday? Are we saying what are we doing here? We're doing 2:30. to 4. That's what we're doing, right? We do that again? All right, everybody got that? And where are we going to be? We'll be here unless we get here and we're not allowed to be, in which case we will all be group panicking. Right? Does that seem reasonable? And then we'll, as a group, we will wander the halls. Yes? Well, hopefully, yeah. I think anywhere except the hall can record. Did I turn it on today? I certainly hope I did. Yeah, we've been going. Yeah. Everybody good? All right, so these slides, you might want to finish them. And I'll see you. Good luck on Wednesday. No. Thank you, everybody. It was a pleasure being with you.